Today, we're diving into something wild. We're going to take nature's oldest, most powerful problem-solving tool, evolution, and see what happens when we give it a serious quantum upgrade.
I mean, really think about that for a second. When you boil it down, our biggest headaches, whether it's designing a tiny microchip or organizing the logistics for an entire city, they're just massive optimization puzzles. And who's the undisputed, undefeated champion of optimization? Nature, for billions of years.
Through natural selection, life is just constantly experimenting. It's testing, it's combining, it's refining countless solutions 24/7. The stuff that works, that survives, gets passed on. The weaker ideas, they just fade away. It's this incredibly powerful, if slow, process. So the big question for computer scientists was always, can we somehow bottle that magic and put it in a computer?
Well, our first crack at it was something called the genetic algorithm. This was our initial attempt to basically copy evolution's playbook and get it running on our regular, classical computers. So here's the cool part. A genetic algorithm doesn't try to find one single perfect answer right out of the gate. No, instead, it creates a whole population of potential solutions, and then it just lets them compete. It lets them evolve, generation by generation, just like in the wild. And this whole thing works in a loop. So first you start with a whole bunch of random potential solutions. Then you test them all to see which ones are the fittest, which ones are actually any good at solving the problem. The best ones, they get to reproduce. Their code gets combined in a step called crossover, and you throw in a few random mutations just to spice things up and discover new possibilities. You just keep repeating that cycle, and with every new generation, the solutions get better and better. It is literally digital survival of the fittest. Okay, so that's the classical playbook. It's brilliant, it works. But what happens when you take that idea and you strap a quantum engine to it? Oh man, this is where things get really, really interesting. To really get the upgrade, you have to look at the absolute basic building block of information. In a regular computer, you have a bit. It's simple, right? It's either a 0 or a 1. End of story. But a quantum bit, a qubit, that's a whole different beast. Thanks to a wild property called superposition, a qubit can be a 0, a 1, or kind of both, all at the same time. It's not logged in, it can explore a whole range of possibilities simultaneously. And this image, the block sphere, is the perfect way to picture it. A classical bit is just a light switch, on or off. That's it. A qubit, though, is more like a point anywhere on the surface of this entire globe. It can exist in this huge, rich space of possibilities between the absolute poles of 0 and 1. And just when you think it can't get any weirder, it does. Qubits can become entangled. This means their fates are linked, connected. If you measure one, you instantly know the state of the other, even if it's miles away. This spooky connection is another quantum superpower we can tap into, letting us build incredibly complex and correlated solutions. So, you take the brilliant blueprint of a genetic algorithm, you combine it with the superpowers of quantum computing, and what do you get? You get the quantum genetic algorithm, or QGA. And as you can see here, it lives right at this amazing intersection of artificial life, optimization, and quantum computing. Okay, so how does this mashup actually work? I mean, how do you really give each step of that evolutionary process a proper quantum boost? Well, the single biggest game changer is how we handle the population of solutions. Instead of a long list of individual attempts, a QGA holds the entire population in a single quantum register. Because of superposition, that one register can represent and explore a massive landscape of potential solutions all at the same time. And here's what that quantum upgrade looks like for each step. The individuals in your population aren't just strings of data anymore, they're qubits in superposition, holding way more possibilities. Crossover isn't just swapping bits of code. Now you're using quantum gates that can entangle solutions in new and complex ways. And mutation? Forget just randomly flipping a 0 to a 1. Now you can use quantum rotation gates to make these subtle, controlled nudges to a qubit state, exploring the possible answers much more finely. All right, I know this all sounds super abstract, maybe like something out of science fiction. But here's the thing. QGAs are already out there, in the real world, solving some really practical problems. And the list of what they're being used for is just wild. I mean, check this out. Researchers are using them for everything from designing smaller, better antennas for our smart gadgets to untangling the massive, complex web of a city's bus routes. They're helping plan emergency evacuations, making cloud computing more efficient, and even getting better at spotting plagiarism. It's amazing. And we're not talking about tiny little tweaks either. Let's go back to that antenna example. One study used a QGA to shrink an Internet of Things antenna by a whopping 87%, and it still performed just as well. That is a massive leap forward, a total game changer. But, okay, let's pump the brakes for a second. This all sounds amazing, right? So it's easy to think the quantum version is just always better, always faster, always more accurate. But is that really the case? Let's get a dose of reality. Here's the million-dollar question. Is a quantum algorithm always the winner? And the short answer, which might surprise you, is no. The reality is, well, it's a lot more nuanced than that. This chart from the research tells the whole story, really. Just look at it with me. The vertical line is how much more accurate it is, and the horizontal line is the speed up. The dream, of course, is that top right corner, where you're way faster and way more accurate. But look where the actual results for different problems land. They are all over the map. Sometimes the QGA is faster but less accurate. Sometimes it's more accurate but actually slower. So what's the big lesson here? It's that quantum advantage is absolutely real, but it is not a magic bullet you can fire at any problem. The real art, the true skill, lies in finding the right kind of messy, complex problems where the unique superpowers of QGAs, that superposition, that entanglement, can really shine and blow classical methods out of the water. And that kind of leaves us with this final, huge idea to chew on. The great challenge of our time isn't just about building bigger, badder quantum computers. It's about a much grander search. A search to look at all of humanity's greatest problems and ask, which one of you has just been sitting there waiting for us to finally combine the ancient genius of nature with the bizarre power of the quantum world?